So we've covered the concept of pressure. We've covered the concept of temperature and volume and how to relate pressure, temperature, and volume using the three gas laws and the combined gas law. One new wrinkle that we didn't talk about was Avogadro's law, which is a relationship between the number of moles of a gas and its volume. Those are directly related. Okay? If you increase the number of moles, you're going to increase the volume. So if we take that relationship and the other three that we learned yesterday, how can we combine them together? Well, let's refresh them really quick. We know volume is indirectly related to pressure. We know volume is directly related to temperature. We now know volume is directly related to moles. So let's put all of the stuff that's directly related in the numerator and keep the stuff that's indirectly related in the denominator. And then what we see here, if we combine this, is that the volume is directly related to the moles times the temperature of a gas divided by its pressure. This directly related, this means some number. What is that number? That number is going to be called the ideal gas constant. And we're going to use the letter R to represent it. So therefore, if we rewrote this equation, if we multiplied by P on both sides and incorporated our ideal gas constant, we would get an equation that looks like this. PV equals nRT. This is called the ideal gas law. And what this tells us is the relationship between pressure, volume, moles of a gas, and temperature of a gas. Okay? What is the value of R? R, this constant, is equal to 0.08206. Units are super important because the value of R will change depending on the units. In this case, for this value, the units are liter atmospheres per mole times Kelvin. So what this tells us is anytime you're using this value of R, 0.08206, your volume better have units of liters. Your pressure better have units for atmospheres, and your temperature better have units for Kelvin. If it doesn't, you need to make the necessary conversions before you do any mathematical relationships. So here is the ideal gas law. Let's get some practice with it. So let's assume that we have a gas at STP. Ooh, what does this mean? This means standard temperature and pressure. What is standard temperature and pressure? Well, it's a set of conditions that scientists do experiments at so that data can be precise and consistent across different experiments. So what are those set of conditions? Well, at STP, the pressure of a gas at STP is 1 atmosphere. And the temperature of a gas is 273 Kelvin. These are the conditions at STP. So if any problem ever says a gas is at STP, you need to know that that means, oh, the pressure is 1 atmosphere and the temperature is 273 Kelvin. So let's assume we have 1 mole of a gas at STP. And we want to know what is its volume. Well, we know the number of moles is 1. We know STP means 1 atmosphere and 273 Kelvin. So let's go ahead and use the ideal gas law. PV equals nRT. Let's plug in our values. Pressure, 1 atmosphere. Volume, we don't know, that's what we're trying to solve for. Moles, we have 1. R, 0.08206. And our temperature of 273. So, if we go ahead and multiply these numbers together, and we're going to have to divide by 1 on both sides, which is the same thing as the answer, the volume that we're going to get is going to be equal to 22.4 liters. Okay. I'm not really paying attention to sig figs right now, but this is a fact. It might be a number that you remember from CP chemistry. If you have 1 mole of an ideal gas at STP, the volume will always be 22.4 liters. Again, something that you need to know. We keep using this term ideal gas, but what makes a gas ideal? Well, let's first think about that word ideal. You know, if you live in an ideal world, you live in kind of like a perfect world, okay? An idyllic world, a place where everything is behaving exactly like you would expect it to. If we're talking about gases that are ideal, they're behaving exactly like we would expect them to. And the cool thing about that is it allows us to calculations to be a lot simpler because we don't have to worry about a lot of different things. There's two characteristics that a gas must have to be considered ideal. Okay? Number one, the molecules, the gas molecules themselves, have no interactions. And by interactions, we mean attractions or repulsions. So if we look at this diagram, you know, we're zooming in on some gas that's in a flask. We see some molecules moving around. Okay. And as these molecules get close to each other, we know that some molecules have charges on them. Well, let's say this molecule here is slightly positively charged, and this molecule is slightly negatively charged. We know that opposite charges are going to attract. So these molecules are going to be slightly attracted to each other. And when that happens, that throws off some of our calculations, because if you remember from kinetic molecular theory, we assume that molecules just move in a straight line unless they bounce off of another molecule. When this repulsion and attraction comes into play, it makes calculations a lot more difficult and tricky. So when we're assuming that if we say that a gas is ideal, we're saying that these attractions don't exist. Think of the molecules just as marbles or balls on a pool table. There's no attraction, there's no repulsion, they just move in straight, perfect lines unless they collide. Okay. Another way of thinking about it is the fewer attractions you have between molecules, the more ideal a gas becomes. So what are some ways that you can decrease the number of attractions? Well, if you make the volume bigger, think about it. If you go from this size to this size, here the molecules are going to be less likely to interact because they're further away from each other. Also, if you increase temperature, if you make molecules move faster, then they're going to just fly by each other. They're not going to have time necessarily to interact. So these are some ways that we can think of gases as ideal. Therefore, the lighter the molecules are, the faster they move, the more ideal they will behave. And the second characteristic that we need to know about ideal gases, number two, is that the molecules themselves have no volume. Which seems a little tricky because if you look at, you know, this molecule here, that molecule is taking up some space in the container. But what we want to assume, sorry for spelling, is that this volume is so small compared to the volume of the container that it almost doesn't matter because it's so tiny. So again, for a gas to be considered ideal, we want it to have no interactions between molecules, and the molecules themselves have no volume. So if there are ways that we can make that more likely to happen, the gas will behave more ideally. If it's not behaving ideally, we say that it's behaving more like a real gas. And therefore, you can do calculations with real gases, but they're just a lot more complicated because there's a lot more details you have to pay attention to. So this is kind of the conceptual overview of an ideal gas, but let's actually apply it to a problem. So here's an example. How many moles of gas are contained in 890 milliliters at 21 degrees Celsius and 750 milligrams of mercury? There's a little typo here. This should say of an ideal gas. So if you're taking yourself, what does that mean? Yeah, it means that these molecules themselves have no volume compared to their container, and that these molecules have no interactions with each other. Also, since it's an ideal gas, that's a buzzword, we're probably going to need to be using the ideal gas law. Well, let's think about what this problem is asking for. It's asking for how many moles. That's N. It's asking, we're given the volume, we're given the pressure, and we're given the temperature. So let's go ahead and plug these numbers in. Well, moles PV equals nRT. We got to remember R is 0.08206 liter atmospheres per mole times Kelvin. Oh, since those units need to be precise, we got to make some conversions. 890 milliliters, convert it to liters. Divide by 1,000, so 0.890 liters. That's going to be my volume. What about temperature? Well, you got to make that conversion. Celsius to Kelvin, add 273.15. So if you do that, you get 294.15 Kelvin. That's my temperature. And then my pressure, I got to make a conversion here. So we know that 750 millimeters of mercury. We know for every 760, there's 1 atmosphere. It's a conversion that we reviewed yesterday. So if we divide 750 by 760, we would get a pressure of 0.9868 atmospheres. Now, let's go ahead and do the actual math where we plug in what we know. Well, pressure, 0.9868 times the volume is 0.890. I'm going to divide by RT here on both sides just to make space a little bit easier. So if I divide by R is 0.08206, and my temperature, 294.15. If I go ahead and do the calculations, I should solve for the number of moles, 0.036. And let's see, how many sig figs do I need? Well, the fewest 3 sig figs look like they're here, 1, 2, 3. So 0.0364 moles of a gas. This is probably the most basic type of problem with an ideal gas. We'll move into more complicated ones in the future, but you need to know how to do problems where you're doing simple substitutions, converting between the units of pressure, volume, and temperature, the qualities of an ideal gas as well.